Welcome to this hands-on video of using structured streaming. In this video, we will continue with the example that we used earlier, which was regarding the international loans dataset. This data was pertaining to loans taken by countries from the World Bank, and the data comprised of all the different organizations which have taken loans, the amount of disbursement, the obligations which are still pending, the interest rates, etc. And there were about roughly 8,700 odd loans that were taken in the data. And this was discussed when we did the hands-on video of how to set up the DataProc cluster and operate on the dataset using Jupyter Notebooks so that it's interactive and very easy to debug. And we used two different approaches. One was using Spark SQL, and the second was using data frame operations directly. So in this video, we will take a look at how we extend that same dataset and use structured streaming. So let's start with, again, the basics of the cluster. So I'm not going to walk through what the cluster setup steps are, because that's already been discussed in that video. But just to show you, the cluster already exists in my case for this example. It's got a configuration which is a default configuration. So the key part here is, two worker nodes, internal IP is set to no. Web interfaces allows me to connect to the different portals which are required for me to work on the data. So Yarn Resource Manager is where I can see the current applications which are running on the cluster. Since most of my applications are Spark, it's helpful to create rather helpful to have the Spark history server also set up on my local browser so that I can take a look at the current Spark jobs which are running. But the most important for our purposes for today is actually the Jupyter interface, because we're going to use Jupyter Notebook again, but use it for streaming programming, which is actually a very interesting way to develop streaming programs in a way that's interactive. So I've already got these opened up. So Yarn application master is here. Let me just refresh this. Rather, Yarn Resource Manager is here. So there's one application which is running right now. Everything else is finished or succeeded or failed. Let me take a look at the Jupyter notebooks which are here. So I'll log into the Jupyter interface of this cluster. Click on GCS, and I can see that there is one notebook which is running right now. So which notebook is that? It's basically the streaming example that I want to walk you through. Okay, so the kernel is already attached to it. So let me start executing one by one. So the first step is basically initiating the Spark environment, and this goes and obtains the resources from the cluster. And if no resources are available because other notebooks are running, then usually this gives a message that says, timed out, waiting for resource to be available or resource to be allocated. So ensure that no other notebooks are running, or you're within the quota of the available resources in your cluster, or you can bump up the cluster size itself. Okay, so then I've got the dataset itself specified in GCS. If you remember from that video, the dataset was downloaded from GitHub, uploaded into GCS in a bucket. I'm going to use the same dataset. Now, in real world streaming examples, the data might not be in a file, or it might be in a file, but that might just be one part of the data. Whereas the real streaming data might be coming in through a live API or through a live website, or in more common cases, a message bus like Kafka. So I'm not going to go through the details of how to set up Kafka, etc. here, but you can follow along. Since you've already done the Kafka assignment, you would know how to do that. But in this case, I'm just going to assume that the same file that's there in the GCS bucket for the batch processing is available for streaming processing. So same configuration file, configuration parameters that I used for batch processing, I'm going to continue to use that. So let me click on this. There is one key change here. I'll come to that when we discuss the next cell. Okay, so for streaming, the critical change, and we saw this in the streaming theory lectures as well, the critical change is how you consume the data and how you uh, produce the data, right? So here the data is actually in a file. For streaming applications to work, you've got to convert this into a stream. But the good part is with Spark, or the interfaces already exist to take a file and treat it like a bounded stream, so that you don't have to, create a brand new stream just for that file alone. So in this case, I'm just going to take that file that exists and directly feed it into the, Spark reading operation, but with some extra information. So first up, because in stream processing, everything is fundamentally a stream, whereas a file is actually a bounded stream. The default stream read interface does not support bounded streams directly. So instead, if you take that particular input file, place it in a directory and feed the directory name itself as the input dataset, then the Spark read stream interface reads the directory itself as a unbounded stream. Now you can ask me, like, why is that, making that an unbounded stream? Because the directory itself has just one file. The reason it becomes an unbounded stream is the directory can have additional files that can come in later on. So while the directory starts off with just one file, and my Spark application starts by reading that one file, because it's a constantly running application, it's always on, it's programmed to expect additional files to be written to it at a later point in time. And whenever that happens, the same program picks it up, right? That's why it is able to treat the directory as an unbounded stream, because of the possibility that there could be additional files. Whereas a single file by itself can never become longer, right? That's POSIX semantics. A file is closed, which means it cannot be added to anymore. Therefore, a single file, which is a single bounded stream, cannot be directly used as the input data set for a stream processing in Spark. So therefore, I'm giving the directory where the file is present. The additional data that I also need to provide, information I also need to provide, is the schema for the file. Unlike sources of data which are supportive of streaming, like Kafka as an example, when it comes to static files, it's important to let Spark know what is the schema that's contained within the file, even though the file itself might have the header row. Now think about it. In this case, the file has the header row as the first row, while the file has additional data rows within it. That is only if you look at it as a bounded stream, where you sequentially consume the input data exactly once, right? One by one, you could just go through. Then you know that the first row is a header row. But in an unbounded stream operation, which is what a streaming operation is, you cannot assume that the header row is going to be present for additional files that can come in this directory at a later point in time. Therefore, the way that Spark resolves this is by asking you to explicitly give the schema when you begin reading from a particular input data directory. So that's what we are doing here. This applies only to static files, by the way, or I should say files which are, themselves placed in directories like this. It doesn't apply to continuous streams of data like message buses. Okay, so the schema that I provide here allows me to read this particular input data the way it was created. So in this case, the schema is created as a struct type. So that's what data schema is. It's a struct type, and that struct type is created from a schema specification string, which is a JSON string. So this JSON string has properties like end of period, loan number, etc., which is the properties which is there inside the data, and it has the types as well, right? String type, etc. For the most part, these are string types which are there. There are timestamps as well. For instance, end of period is a timestamp. So this schema was generated programmatically by me by looking at that data set as a single machine Python program. But you could hand code the schema as well if the number of columns is small, or you can use other programmatic methods to generate the schema. Anyway, so the schema string is given here, that it's converted to struct type and it's provided as schema information in order for the read stream to be executed. The read stream is practically like the spark.read function. It's just that the interface now allows for streaming, right? Once I execute this, sorry, I'm not executed this yet, so let me execute this now. Yeah, so it's done. At this stage, I have now created a data frame which is called as df loans. I've just created a suffix _s to indicate that this is a streaming data frame. The rest of the operations that I want to do is very similar to what I did for the batch processing case. So first up, I want to convert some of the columns which I work with so that it's easier for me to refer to it without spaces in the names. So the with column renamed is a function that continues to be available. So I use that. So let me run this. Then I use data frame operations in order to execute my aggregations that I want to do. I could have used SQL as well, not a problem. So in this case, it's a group by per country, and I want to total up all the obligations which are pending, total up all the disbursements which have been made by World Bank, and the average interest rate. So the ag function continues to apply with a custom JSON specification, and the names of the columns which are returned as a result are complicated, so I want to make it simpler for me to refer to it. So all of this applies exactly the way it was in batch processing, and that was the benefit of streaming using Spark, right? That's what we spoke about in the theory. Okay, so again, these are transformations. There is no action that's performed yet, so nothing is actually executed. I've finished the cell. Now comes the output side of streaming, and here's again, some nuances that will vary from batch processing. First and foremost, I want to know where do I want to produce the output. Unlike in the case of batch, where I want to concretely produce the output in a file, because this is a streaming function or streaming operation, it continuously produces output in a place which supports continuous output production. So which means it would need to provide a streaming output mechanism or capability. So I don't want to use GCS for that, because GCS again is bounded streams or bounded files. So instead I just want to produce the output in the console, and console here refers to the Jupyter Notebook itself. That's point number one. The second point is, when I produce the output in the console, I can control the output mode. So which means as new data comes in, if my aggregated output in this data frame, like in this case the total disbursed, total obligation, average interest rates per country, if that changes because newer data sets have come in, then do I reproduce the aggregated values for all the countries or only for the country which is changing? That's what's controlled by the output mode. In this case, I'm just specifying output mode as complete, which means it produces the aggregations for all the countries. And with that, I'm ready to start. So I encapsulate this within a query processor, which takes this streaming data frame and writes the stream. The key variable here is, rather the key function call is here is a start function call, which will basically trigger the entire execution of the streaming engine. But all of this gets triggered only when you also specify the stopping condition. So here the stopping condition is basically, wait for 120 seconds and then stop. So that's what I've done here. I've specified the stopping condition. I've started to execute. So now as it executes, you will find that the output mode being complete and the format being console means that this particular cell will always run, and it will keep refreshing as new data set keeps getting added to it. So let's just give it a few minutes for the first execution to run. There we go. It says batch 0, which means this is actually the first execution of the streaming function. And in this batch 0, it's produced the aggregated output for all the countries. So I'm not limited to top 25, and it's not in any particular order. So it's come up with all the different countries, but it's showing only the top 20 rows here. Now notice that this cell continues to run, and that's because the stream continues to be alive, which means for as long as the stopping condition is not not hit, this streaming window continues to be active, which means I can now add more files to the directory and it will produce newer outputs. But at the end of 120 seconds, in this case, it will stop this particular query execution. So let me stop right now with this example. So hope you got a sense of how structured streaming can be also executed using the familiar interface of a Jupyter Notebook, working with real world data sets, and on top of like simple DataProc cluster configurations that you can avail of at a very low cost. As you scale up the datasets to much larger volumes and presumably at higher velocities, you would need to also incorporate the other components that we've already touched upon, which are message buses for holding the data in a transient manner, as well as other monitoring mechanisms for outputs of the data processing. Like for instance, you could produce intermediate aggregates, or you could produce like 2 or 3 different types of outputs, each catering to different use cases, and each of those data frames being written to different destinations, like for instance a database table, while the main streaming operation continues to run in an always on fashion. So those combinations of complexities are also perfectly possible. Spark is extremely good at giving you that power. Thank you, and wish you the best for the OPP